As we saw in the previous lecture, a quantum algorithm can be expressed by using a high-level programming language. However, this is still the human talking to the machine, and our quantum processor doesn't understand such a language. That's why we need a compiler that translates an algorithm written in a high-level language into a lower-level language or machine instructions that can be executed on a particular hardware, in this case, our quantum processor. Usually, a quantum compiler generates what is called quantum assembly language, or QASM, that is ultimately converted into a binary executable code. However, the mission of the compiler is not only to produce this low-level code, but also to manipulate the quantum circuit to get a version that is runnable on the quantum chip. By runnable, I mean a circuit version that takes into account the details of the chip, such as what operations it supports or what constraints must be respected. To this purpose, the compiler will perform several tasks. It will decompose the quantum gates. It will optimize the quantum circuit in order to reduce, for instance, the number of qubits or the number of operations. It will schedule the operations to maximize the parallelism of the algorithm. It will map the quantum circuit to that the constraints of the chip are satisfied, and it will create a fault-tolerant version of the circuit. So let's explain all these steps by showing some examples. As mentioned, one of the tasks of the compiler is decomposition. Any unitary gate, single qubit or multi-qubit gate, needs to be decomposed into a reduced and discrete set of gates that are universal. One of the most popular fault-tolerant universal set is called Clifford-T. That includes, for example, the Hadamard, CNOT, S, and T gates. Here, you can see an example in which a Toffoli gate is decomposed in a circuit that consists of Hadamard, T, T-dagger, and CNOT. However, this circuit cannot be run yet on the quantum chip. We still need to go one step further and express such a circuit in a series of elementary or physical operations that our hardware can support. For instance, a CNOT is decomposed into two Hadamard and a C-phase gate. The compiler can also perform some optimizations of the circuit. As I just mentioned, circuit can be optimized in order to reduce the number of qubits required, also known as width of the circuit, or to reduce the depth of the circuit or number of gates. This optimization can be performed at different levels. It can be done at the high-level description of your circuit, in which, for instance, it identifies the QFT and it inverts and it cancels them out, or it can also be done at more elementary level after the gate decomposition, in which two Hadamard cancel each other. Another function of the compiler is the scheduling of operations, and this is crucial when the target platform is your quantum chip. Minimizing the circuit latency or execution time of the circuit helps to reduce the potential of having errors during computation. In order to schedule the quantum operations, a quantum instruction dependency graph is built. In this graph, the circuits represent instructions or operations, and the edges represent the dependency between them. Based on this graph, different schedule techniques can be used, such as soon as possible or as late as possible. In our example, the operations have been scheduled using an as soon as possible technique, and this is the resulting circuit and the corresponding instructions. In our case, 6 cycles are required for the execution of the circuit. Another part of our compiler is the mapping of quantum circuits. In order to run an algorithm on a quantum chip, the corresponding circuit needs to be mapped onto it in a way that the constraints are satisfied. One of the main constraints in experimental platform is the limited connectivity between the qubits. That reduces the interaction between them, for instance, to only nearest neighbor. In other words, only the qubits that are neighboring to each other can perform a 2-qubit gate. Here, you can see an example of a simplified layout of a 7-qubit chip. Each circle represents a qubit, and each arrow the possible interactions between them. Now the question is, where are the qubits in my circuit that we call virtual qubits placed in our quantum chip? Or in other words, what virtual qubits correspond to what physical qubit? This brings us to the first step of the mapping process, that is the placement of qubits. For instance, we can map the virtual qubits to the physical ones in this way. One can try to place the qubit in a way that all connectivity constraints are satisfied and all the interactions between them are possible. However, it's not always possible to find such a placement, in which, again, all the constraints are satisfied from the beginning. This means that non-numbering qubits, or qubits that are not connecting to each other and need to be moved or routed to be placed in adjacent positions in order to perform a 2-qubit gate. This movement or routing of qubits requires extra operations that need to be inserted into the circuit, as I will explain in the next example. Just to mention that different operations can be used for doing this kind of movement of qubits or quantum states. For example, swap operations in which the quantum states are exchanged, like this the one used in superconducting qubits, or the shuttling used in spin qubits. If we look at the example, if we're going to perform a CNOT gate between qubit 3 and qubit 4, that is possible as there is a direct connection between them. If we move to the next CNOT, and now we're going to perform a CNOT between qubits 3 and 5, again, this is also possible because those qubits are neighbors. However, if now we want to perform a CNOT between qubit 2 and qubit 4, they are not neighbors, and they need to move to adjacent positions. This can be done just by swapping Q3 and Q4. And now, as you can see, Q4 and 2 can interact and perform such a CNOT. It is clear from this example that the routing of movement of qubits produces an overhead in terms of not only the number of operations, but also in terms of execution time of the circuit. That communication overhead will affect the reliability of your quantum algorithm. Therefore, an efficient mapping in which highly interactive qubits are placed next to each other, combined with smart scheduling techniques and routing techniques, will help to decrease the failures on your computation. Finally, another task of the compiler is to translate this high-level description of your circuit for the algorithm into its fault-tolerant version. As you know, quantum bits are error-prone. That means that they easily lose their state due to the interaction with the environment, and therefore, quantum error correction and fault-tolerant techniques are required. A logical qubit is encoded into several physical qubits, and the system needs to be continually checked in order to detect and correct possible errors. The use of quantum error correction will substantially increase not only the number of qubits that you will need in your algorithm, but also the number of operations. As it was mentioned in the first part of this lecture, there are several compilers for quantum computers, such as ProjectQ from ETH Zurich, SCAPCC from Chicago University, Liquid from Microsoft, and our OpenQL compiler that has been developed here at QTech. All of these compilers generate a kind of quantum assembly language, or QASM, that can target different backends. Those backends can be a simulator used to simulate quantum computation, or it can be real quantum processors, such as the one that we are developing here at QTech, or the ones from IBM, Rigetti, or Google. So just to wrap up, in this lecture, we have learned that in order to express our quantum algorithm, a high-level programming language is needed. A compiler will translate this high-level description into executable code that will make the required optimizations and transformations to obtain a circuit that is runnable on your quantum chip. These quantum instructions are part of what is called quantum instruction set architecture, and they will be sent to the microarchitecture for the execution on the quantum chip.